Okay, we have discussed about the random process, and then we have classified it into two categories, stationary and non-stationary. So in the stationary process, we have seen that the ensemble averages, they are independent of time. Okay, and if that condition is not satisfied, we call it as non-stationary process. And then we have a special type of stationary process, what we call as wide sense stationary, in which the mean of the random process is constant and it is independent of time, and the autocorrelation between two random variables observed at t1 and t2, that depends only on the lag, which is the time difference between the two intervals. Okay, this is what we have discussed. Okay, so we have defined the mean of the random process using this relationship. So statistically, to define the mean, you need the PDF of the random variable at each and every instant of time. Okay, but if that PDF is not available, we have used ensemble averages. So we have a set of function, and the mean of the random process at time t naught is nothing but the mean of the sample values that you have observed, and so on. Okay, and we say that when this mean is independent of time where you are observing this random process, then we call this process is first order stationary. Okay, it means the random process, the process is random, but the randomness is somehow uniformly distributed. Okay, so that the mean remains same, and the autocorrelation depends only on the difference t2 minus t1. This is what we have discussed in the last class. Stationary, there is another process which we call as ergodic random process, which is basically a special type of stationary process. So you will see that to find the mean and the autocorrelation, we need an ensemble. Okay, a set of functions which comprise the ensemble of this random process, and from this ensemble we estimate the mean and the autocorrelation function. But practically, if you see, we don't have a set of measurements of the random process. What is available to you is one function of time. Okay, is one sample function, you can say. So this is a sample function from this random process. Okay, any one observation, either this or this or this. Okay, so in such a situation, instead of defining the ensemble averages, you define the time averages. Okay, it means if I define the time averages, then the mean of this function, if I say this function is x kt, any kth sample function from this set, then its mean will definitely be mu k will be integration of x kt dt minus t by 2 to t by 2 divided by t, and the limit t goes to infinity. Okay, it means I am finding the mean of this sample function by integrating it from minus to plus infinity and then dividing with this infinite time interval. Okay, and if the function is discrete in nature, the discrete random process, and we have one sample observation, definitely you can find the mean of the random process from this single observations, that is sum of all the samples divided by total number of samples. Okay, so like for the continuous, you have to integrate it over the entire time interval divided by the total time. This is what is called as time average. Okay, and likewise you can define the autocorrelation. So if you have just one pulse, one sample function, then the autocorrelation of this sample function will be, for kth sample function I am saying, it will be integration of xk of t into xk of t plus tau into dt minus t by 2 to t by 2 1 by t limit t approaches to infinity. Okay, so in the ensemble autocorrelation, what we have done is that you are multiplying these two samples. This is the random variable x, which is the random process observed at t1, and this is another random variable at t2. So when you find the correlation between these two random variables of the same random process, we call it as autocorrelation. And what we have done in the sample average is we just multiply the corresponding samples and then we have find their mean value or the average. Okay, but now since you just have one sample function of the random process, not the set of functions, so you just take one measurement or you have one observations and you are trying to find the mean and autocorrelation from this. So in that case we are using time averages. So this is called as sample mean. Okay, and this is called as a sample autocorrelation. So if you observe this equation, it is basically, this is xkt, that is the kth sample function. It can be x1, x2, anything. So xkt and xkt plus tau dt, and it is a function of tau. Definitely, it's a function of lag. So what actually you are doing is that you are shifting the sample function, and then you are multiplying this sample function with itself, and then you are finding the integration and the average value of that. That is how you are getting the autocorrelation, or we call it the sample autocorrelation. Okay, so you take one function x of t and then you shift it by some time tau, which is lag. So if tau is positive, it is shifted to the left. If tau is negative, it is shifted to the right. If I suppose say this is t, this is x of t, then x of t plus tau will be a time shift in this function. Okay, so this origin, if I say this is tau is suppose 1, then definitely x of t plus 1. Okay, so this signal will be shifted by 1 to the left. So the origin will be shifted to this point. And then you are multiplying this. Okay, and then you are finding the product and then integration and then the average of that. Okay, that is how you get the autocorrelation if you have a sample function. Okay, and it gives you basically the degree of similarity of the function itself. Okay, like suppose if I take a pulse like this and I have another pulse. Okay, so this is one pulse, this is another pulse. If you keep this pulse fixed and you go on increasing, this is suppose x of t, and if I say this is y of t, so if you shift it by some time tau and then multiply with this and integrate. Okay, so as long as these two pulses that don't overlap, your integration will result in a zero value. And when you go on increasing tau and it reaches here, suppose, then you have some overlap maybe between these two pulses, and then in the integration you will get some area. Okay, likewise when you increase the tau and it reaches here, so they may be exactly overlapped. So at this time you will get the maximum correlation. Okay. So when you plot this autocorrelation, it is basically a function of tau, which we call as the lag parameter. Lag simply defines that by how much time you are shifting the pulse with respect to itself. Okay. So and for each value of tau you compute the autocorrelation and then you plot it. Okay. It may take any shape. Maybe suppose for tau is equal to, definitely when it is autocorrelation, when tau is 0, you will get the maximum value, because in that case you are simply multiplying the sample function itself. Okay. So it starts from the maximum tau is equal to 0, and then as you go on increasing tau, this value will decrease. Okay. Maybe like this. This is what is the autocorrelation. Okay. That you obtained from a sample function. So when you say that the process is ergodic, that means that your ensemble averages and your time averages, they are basically same. Okay. It means if I say this process is stationary and it is also ergodic, then whether you compute the mean from this sample function or this function or this function, that is going to be the same. Okay. Similarly, the autocorrelation that you compute using this sample function or using this sample function or this function, that will be same. Okay. And that will be basically equal to the autocorrelation of the random process at that lag. Okay. Like if the process is stationary, then its mean is constant. Okay. You have E of xt, which becomes mu, constant. It is independent of time. And if you say that the process is ergodic, in that case the sample mean is also equal to mu, and that sample mean is independent of whether you compute from this sample function or this. Okay. So if we assume that any process is ergodic, in that case the mean and the autocorrelation of the random process, they can be computed from a single observation. Okay. So there is no need to have multiple measurements and you have a set of signals from which you estimate the mean in the autocorrelation. Okay. So ergodicity implies that your sample mean is equal to your ensemble mean. Okay. And similarly, your sample autocorrelation function is equal to your ensemble autocorrelation function. Okay. So you have one signal, and from this signal you compute the mean of this sample function, and the mean of the sample function will be same as the mean of the random process. Okay. Because the random process is already stationary and its mean is constant. It is independent of time. And similarly, your autocorrelation will be a function of lag. Okay. This is what we call as an ergodic process. And this autocorrelation function is important, you can say, statistics that we use in computing the power spectral density of the random process. Okay. So if you see the PSD or power spectral density, we will show that the autocorrelation function and the power spectral density, which you may denote with x of f, they form a Fourier transform pair. Okay. It means if you take the Fourier transform of the autocorrelation of the random process, you will get its power spectral density. Or if you take the inverse Fourier transform of the power spectral density, you will get its autocorrelation function. Okay. So before going into the details of this, uh, let us recap about this PSD, or in fact, first let's say about ESD, which is energy spectral density, and then corresponding we have power spectral density. Okay, so this is for the energy signals, this is for the power signals. So you already know how you define the energy and the power of the signal. So if I say I have a signal x of t, then the energy of this signal, if I say Ex, it is given by integration of x squared d dt. Okay, that is how you define the energy of the signal. And in the frequency domain, using the Fourier transform, you can use the Parseval's relationship, and this can be expressed as minus 2 plus infinity x square f df. Okay, or in fact mod of x square, this should be here, x square f df. Okay, where xt has a, where xt and your x of f, they form a Fourier transform pair. Okay, so this is what you know from the basic theory of signals and systems. Okay, so if you have a signal which has a finite energy, then definitely it must be uh, time bounded, then only it will have a finite energy. Okay, and its energy is given by this integral of x square t dt, and the sum can be computed in the Fourier domain using its Fourier transform, that is mod x square df. Okay, so this term mod of x of f square, we generally call it as the energy spectral density. Okay, ESD. Because if you see that the total energy of the signal x, E of x, that is nothing but the integration of this. Okay, so if you integrate it in the frequency domain over minus 2 plus infinity, you get the total energy of the signal. So definitely this is going to represent the energy spectral density, or you can say the energy per unit bandwidth or per unit hertz. That is what is represented by mod of x square. And integration of this over the entire interval, you will get the total energy of the signal. Okay, and this is a very common relationship which is used to find the bandwidth, or it is used to estimate the bandwidth of energy signals. Okay, like suppose if I say that I have a rectangular pulse. Okay, a rectangular pulse, the pulse width of t may be t by 2 to minus t by 2. This is x of t, amplitude is 1, and if you find its Fourier transform x of f, it is going to be a sinc function. Okay, and if you take mod of that, mod of x of f square, so you get only the positive values because of this square, so you will get something like this. Okay, symmetric. So ideally, if you see the bandwidth of this pulse is infinite, because your sinc pulse will extend from minus to plus infinity. Okay, but for practical reasons, we take the bandwidth of this pulse as finite. So that bandwidth will depend upon that how much energy basically you are taking under the energy spectral density. Okay, suppose if I say the bandwidth as the range of the frequencies which contains the 90% of the energy of this pulse, then you will get V as 1 by T. Okay, so if you take a bandwidth of 1 by T, that 1 by T hertz bandwidth will contain around 90% of the pulse energy. So that I can take as the estimate of the bandwidth, or you can take 95% or 99%, whatever you want. Okay. The more energy you take, the more bandwidth fact you have to take in the frequency domain. Okay. Now for the power signals, uh, you define the power spectral density, or before this PST, we can also show that the energy spectral density and autocorrelation function, they will form a Fourier transform pair. Okay. So if you have a pulse x of t, its autocorrelation function, you can say maybe r of tau will be integration of x of t into x of t plus tau d tau. Okay, because I am taking this as an energy signal, so it is finite in time. Okay, time is bounded, it cannot extend from 0 to infinity or minus 2 plus infinity. So that is why that averaging divided by t and limit t approaches to infinity is not here. Okay, so you are simply shifting this pulse by tau, then you are multiplying itself and integrating it. That is how you get the autocorrelation of this pulse. Okay, and you can simply show that if I find the Fourier transform of this autocorrelation function, that will become the power spectral density. Okay, so the Fourier transform of this, the Fourier of r of tau will be equal to integral of the Fourier transform of this will be, say, Fourier of, if you say Fourier of r of t, then that will be integral of r of t into e raised to power minus j 2 pi f t dt. But since it is a function of tau, you will have r of tau multiplied with e raised to power minus j 2 pi f tau into d tau. Okay, and this r tau can be taken as this function. So we have basically minus 2 plus infinity. You will take e raised to power minus j 2 pi f tau multiplied with r of tau, which is this in either integral. We have x of t into x of t plus tau dt. Okay, sorry, this should be t here. This is not tau because it is a function of tau. So this t will cancel out in the integration. It's a dummy variable. Okay, so dt then multiplied with d tau. Okay, so Fourier of rt is this, then I can say that the Fourier of r tau will be integration of r tau e raised to power minus j 2 pi f tau into d tau, and this r tau, which is the autocorrelation, is replaced with this equation. Okay, and you can manipulate this equation as minus 2 plus infinity. You can take x of t into second integral multiplied with x of t plus tau, or I can write it as tau plus t e raised to power minus j 2 pi f tau into d tau, then multiplied with the d of t. Okay, so you can make this simple modification of this equation. It remains same. And now if you look to this integral, this is the Fourier transform of x of tau plus t. Okay, the Fourier transform of x of tau plus t, because in this integration you have your tau and then you have your d tau. It means you are finding the Fourier transform of x of tau plus t. if you just find the Fourier transform x of tau, it is x of tau e raised to the power minus j 2 pi f tau d tau. But it is tau plus t. It means I am finding the Fourier of basically x of tau plus t. And if the Fourier of x of tau is x of f, then you can use the time shifting property, and this will become x of f into e raised to the power j 2 pi f t. So this integral can be replaced with x of f into e raised to the power j 2 pi f t. Okay, and then what you are left with, integral of x of t into x of f e raised to the power j 2 pi f t into dt, and you can take this x of f outside the integration. So what you are left with is x of t into e raised to the power j 2 pi f t dt, and this is x of f into x of minus f, because x of f is x of t e raised to the power minus j 2 pi f t. Okay, and if you replace this f with minus f, you get this minus j will become plus j. Okay, and for the real signals, your x of minus f is the conjugate of x of f. So when you multiply these two, you will get mod of xf square. Okay, so which is nothing but the energy spectral density of x of t. So the Fourier transform of the autocorrelation function and its energy spectral density, they form a Fourier transform pair. Okay, and the same thing we can do for the power signals. Okay, this I am talking about the deterministic signals, not about the random process. Okay, and you can extend the same concept later on to the random process.